So here is another example, okay, in which I will explore with you, the application in which we needed really a small input resistance, okay. And as I said, usually this happens when you, interface to, an antenna or, coaxial cable in which you have very low input resistance for such devices, okay. So the equation, the problem here is that we have two stages. Again, we have first common source amplifier, then we have a common gate amplifier. Common gate amplifier, okay, and between there is a coaxial cable, just a cable, okay. But the problem with the coaxial cable, when the signal flows through it, it's usually make there will be a kind of, you can say, radiation or something. So the radiated signal may make reflections and stuff. So you may have losses inside the coaxial cable, okay. We will not care about the internal operation of the coaxial cables right now, but what we need here to know is the equivalent resistance of this coaxial cable, okay? Because these reflections will be minimized or even reduced to zero if we interface this coaxial cable to a circuit, and this circuit has input resistance equal to the input resistance of the coaxial cable, okay? So let's read together the problem and see what's really required and what's really given here. So this circuit shows the scheme for a coupling and amplifying a high frequency pulse signal. So we have here our input signal, which is high frequency pulse. High frequency usually have radiation and stuff, and reflections, okay, and of course losses. The circuit utilizes MOSFETs whose bias details are not shown. So these two common gate and the common source circuit has of course the biasing, but the biasing are not shown, okay, and we will not need it. We have a 50 ohm coaxial cable between the two stages, okay. And when we say 50 ohm coaxial cable, that means that the input resistance here of that guy is 50 ohm. For proper operation of that circuit, okay, transistor Q2, this is Q2 here, the common gate, is required to present a 50 ohm resistance to the cable. So the input resistance of the second stage here, and remember, common gate means the input is at the source. So here is the source. So when we look between the source and the ground, we should see 50 ohm. If this guy, for example, the coaxial have 100 ohm, so the input resistance of the common gate should be 100 ohm. So to minimize the reflections, of course, to minimize the losses. Okay. Number one, find GM2. Find GM of that transistor Q2. Okay, so let's do that. Okay. So let's draw the equivalent circuit of the common gate alone, without the coaxial cable or the first stage. So it will be something like this. You have here GM VGS. Here is the drain. Here is the source. Then 1 over GM. And GM2 in that case. And here is the gate, and the gate is connected to ground. Okay, and the drain is connected to ground through RT. And here is VO. Good. So I will not draw the rest of the circuit, which is connected to the source, the coaxial and the first stage. But let's ask ourselves a question here. So what is our input here? So this is our input 2. And we said that it's required for Q2 to have, or the stage 2, to have input resistance equivalent to the resistance of the coaxial cable. So our input 2 is equal to 50 ohm. But what is our input 2 here if we look between these two terminals? This is and the ground. So our input 2 is also equal to 1 over GM2. So 1 over GM2 is equal to 50 ohm. So GM2 is equal to 1 over 50, which is 20, I think, millimho or milli ohm minus 1. Yeah, 20 milli ohm minus 1. Good, that's A. So let's go to B now. If Q1 is biased at the same point as Q2, since they have the same biasing, they should have the same current. So same biasing means same current. So ID1 is equal to ID2. What is the amplitude of the current pulses in the drain of Q1? And here I write it for you guys. I small, D small. Maximum. The amplitude, I mean the max amplitude of the current in Q1. So what's required here is I D max. Remember, when we amplify something, we have the biasing, which is DC, and superimposed on that DC there is EC. And what's required here is the maximum current, the maximum AC current, without the portion, the DC portion. Okay, good. So let's go back a little bit and make the analysis again of the small signal inputs. You remember, guys, from not the last lecture, the lecture before the last lecture, we made this analysis. We said that usually the inputs are small in amplitude. So let's see what kind of approximation we can make based on that assumption, which is a correct assumption, a very valid assumption. And we find that we can decouple the DC from AC. So let's do it again. So ID, I small d capital, means AC plus AC, equal to ID1 here, equal to Kn over 2 V small GS capital minus V threshold square. Remember, it's required in that question here ID maximum. ID maximum will happen when the voltage at the gate here go to maximum. So this happens at VG maximum. Remember here Vs is equal to 0 all the time in AC or DC. Okay? So this is equal to Kn over 2. This is VG maximum minus V threshold square equal to Kn over 2 again. And then V small G maximum is V capital, G capital, the biasing voltage, the DC biasing voltage of Q1, plus V small G small, which is V input maximum, by the way. The input here, this is V input, minus V threshold square. Okay, this is equal to Kn over 2 again. And then I will take VG capital, V threshold the capital as a one term, and add here VG max square equal to Kn over 2 again. And then I'm sorry, there is no square here. Then I will make the squaring. So this is VG minus V threshold square plus VG max square plus 2 VG max VG minus V threshold. Okay, this is equal to Kn over 2 multiplied by this guy, VG minus V threshold square plus Kn over 2 VG max square plus 2 kn, because kn over 2 multiplied by 2 will go by 2 with half. So kn Vg max Vg minus V threshold. Good. What is this? This is ID capital. Okay. This is the biasing current, the DC biasing current of Q1. Plus Kn over 2 Vg max square plus Kn Vg max. And yeah, and what is Kn Vg minus V threshold? This is Gm. So the third term, this is Gm basically. So the third term will be Gm Vg max. And remember, for a small signal model, in the small signal, Vg max square is assumed to be much larger, smaller than the first term, which is, you know, Vg minus V threshold square. So we can basically neglect Vg max square. So this can be neglected, So based on that, ID, I small d capital equal to ID all capital, plus this will be neglected, Gm Vg max. This is DC, and this is pure AC. Okay? So ID, I small, D small max is actually equal to the AC portion, which is Gm Vg max. Gm is known, 20 millimho, ohm minus 1. Mho is ohm minus 1. Multiplied by Vg max. And what is Vg max? Vg max is, if we look here, it's 5 millivolts. Okay, and remember here there is also milli, so it will be in micron. So ID max basically is 0.1 milliampere. That's what's required in B. And C now is connected also to B. So basically the same question, but another requirement. So what is the corresponding amplitude and voltage pulse at the drain of Q1? So number C, basically it asks for what is VD max. Now I'm gonna draw again the equivalent circuit of the first stage, because we need only AC voltage here. So gate 1, drain 1. I'm sorry, this is gate 1. Here is the source of the gate. So usually common source amplifiers, we draw the original version of the equivalent circuit. Source 1. Source is connected to ground. Between gate and source, there is open circuit and a voltage VGS1. Then you have the input, VG, or VGS, S is 0, so it's VG. Now, between the drain and the ground, we're going to see what we can see. We see here the input resistance of the coaxial cable, or input coaxial. Our input coaxial, which is 50 ohm. So we can just remove the coaxial and, you know, the second stage and put just 50 ohms, and we're fine. And now what's required is VD max, VD1 max. Because again, we are talking about the first stage here. VD1 max. We know ID1 max, which is the current flows here. So ID1 is flowing into our input. So VD max is basically, VD1 max is equal to ID1 max multiplied by our input coaxial. So VD max, equal to 0.1 milliampere multiplied by the 50 ohm. We can leave it by as ohm, and the result will be in millivolt. So this will be 5 millivolt, the maximum output that we can see in the common source stage. Okay, guys. So see you next time.